figure this out by myself. I don't know if anyone in here would figure it out by themselves. So, yeah. All right, go for it, Madeline. Figure it out. You can go out in the hall and figure it out while the rest of us work on it.
Absolutely not.
All right. So this is the one that I showed you yesterday, right? 1 to the infinity power, but we knew it approached something between 2 and 3. So let's take a look at how we're going to deal with this. Hey, if we have to have a ratio of 0 over 0 or infinity over infinity, we got to get that thing out of the exponent. What operation do we use to get things out of exponents?
Logarithms.
So let's define a dummy variable real quick. Pick your favorite letter. I'm gonna use Y. Because it's my favorite letter. Just to kind of turn this, make it just to give us something to work with here. Welcome back. And then, you know how you can derive both sides of an equation? You can multiply both sides of an equation by 5. You can add or subtract numbers. You can antiderive both sides of an equation. You just have to solve for C. You can take the logarithm of both sides of an equation, or you can raise both sides of the equation to an exponent. So let's take the natural logarithm of both sides here real quick.
Oh my, dude, leave me alone. Leave me alone.
This will allow us to then use the logarithm property, which gets the exponent out of the exponent. Gets the exponent out of the, bring the exponent out. Well, if we were to try and do the limit right now, what would we have? Not a good answer, but what would we have? Infinity times natural log of 1 is 0. So we basically have infinity times 0. Hey, that's another one of our indeterminate forms. Weird. Okay. Well, we needed a ratio no matter what. Any ideas on how we could turn this into a ratio?
You could do ln y.
Then we have subtraction. And then I'm worried about having 2 variables too.
Derive it.
I don't want to derive it. No. If there's multiplication, then you can turn it into a ratio.
What about
Do what? Or project?
Yeah.
What I do?
You should divide the natural law.
It would turn into, if the inside of the ln's was divided, you could make subtraction.
Would you multiply it by 8 to the
Substitute the natural log of y for that.
How about let's just abuse one of those old exponent rules again. You heard me. Let's use the negative exponent rule. Let's check and see what we have. We know if we try and plug in infinity, we get natural log of 1, which is 0. And then the inverse of x, or the reciprocal of x, well, if you plug in infinity there, you get 1 divided by infinity. That's also about 0. So, hey, we have 0 over 0, and we try and evaluate the limit. I never actually rewrote the limit, so squeeze that in there real quick. Boom, there we go. If I try and punch in limit as x approaches infinity, I got 0 over 0, which is an indeterminate form. So we can finally use L'Hopital's rule. I'm gonna work with just this right side here. So forget about the natural log of y for now. Don't forget about it forever, just for now.
Where'd you get that?
Negative exponent rule on this guy. I need to have a ratio, so I had to force something divided by something.
Wouldn't you have to do that to the ln y too?
Not if I want to leave it. No, I'm just doing it on the right side of the equation. Well, I guess that's 0 over 0. So now let's use L'Hopital's rule here. All right. Let's derive that inside, or the logarithm. So let's see. Well, it's always 1 over inside. Hey, I'm going to rewrite this as x to the negative 1, if that's okay. Thanks.
I give
And
you
then-
express permission.
The inside's not just x, so we got to chain rule it. Times derivative of the inside, which would be there we go. Cool. Okay. And then now we got to derive the denominator, which, okay, hey, we already did that one, so we can reuse negative x to the negative second power. Is this a limit we could evaluate? Can't we just what? Yeah. Hey, these terms are identical. It's multiplication division. You got to believe in yourself. If you don't believe in yourself, no one will. We punch in infinity over here. What do we end up with? Over. I mean, that's a bad thing to write infinite equals on. How about I'll just do yield? Yeah, I think it ends up being 1 over 1. So this limit is 1. But remember, that was not our original problem.
Oh, no.
I'm now going to resume where we underlined in blue. I know, right? So I'm coming back to the left side of the screen here. Limit, as x approaches infinity, of the natural logarithm of the thing we started with is 1. What's the limit as x approaches infinity of the actual thing we started with?
Oh, let's go.
How do you get out of logarithmic form?
Base E.
Log base answer equals exponent. Your base is e. Your answer is y, which I'm keeping over here, and then your exponent is 1. So the limit of the thing we started with is e to the first power.
Why do we have to do all this if we do 1 to infinity is e?
It's not always e, my dude.
It's like it goes to e.
It could, but it doesn't. This one does.
Why? But the graph went to e.
Right. Well, because it was a graph of this exact limit.
So if we plug in like log 3, we still get e.
Yeah, you just have to use the change of base formula to get it. Yeah.
So would you always use natural log?
Always use natural log. That's just how I was trained. Because if you don't, I think you're going to have to use the base change formula, which who wants to do that? Whew. One more for good measure. Oh, I don't. I wish I hadn't picked this problem because it's the same style. I intentionally tried to give you a different one and I failed. Well, you try this one.
Oh.
Here, I'll put this one back on the screen so you can see how we did it the first time. Try the next one on the next page. Is it? Yeah, oh, yeah. It's x to the power of quantity 1 over x minus 1.
So is it 1 over x minus 1 or 1 over x?
1 over x minus 1. All of that in your exponent.
Oh, what? Okay. Is it?
I will write it on the board. I will write it on the board. Yes, I apologize for the poor formatting here. This is x to the 1 over x minus 1. There we go.
Yes, it does. No, it doesn't. 1 minus 1. Yeah, 1 minus 1 is infinity.
You guys.
No, I gotta run the actual test right here.
Oh,
Correction.
that's exactly.
Yeah, we got two wrong.
That's unfortunate. Yeah.
I will.
You haven't taken that test yet, though. You have that test.
It's stretched out over a year. That class is all semester. So like, it's hard and there's no instructors. So it's all but you've got plenty of time to work on it. But I was asking, I mean, John Ferris has been reneging about their experience. So,
Zero. Bam, bam, bam. Bam, pow. Oh, this one isn't that bad. Yeah, come on.
yes, this will be another one.
I'm sorry. I apologize.
So for all you guys, put it down there.
This is awesome.
Exposure classes. You know the guys right now. It's all online. Kind of tough. One upside is in college, that's a 1 semester class. In high school, it's a full year. So at least you do, even though you don't have the physical teacher in the room, you have to email back and forth. You do get the extra time to like process. So, if you didn't want to take that, AP Stats is a great class. Oh, you probably already did it.
We already did it.
He had
Okay. All right. So, or if you really want to slum it, you could go back to college.
Hey, let's go.
So I think I found our goal for next year.
No.
No.
Actually,
No way. He's probably gonna go with Juco.
Joko. Yeah, I call Joko.
Joko?
Wait, are you?
Johnson County Community College?
No, I call it JCCC. Why do you call it Juco? Why Juco? There's no U.
No, that's what everybody calls it.
I thought you meant like just like Johnson County. Period. I call say Joko.
I don't know.
Say Joko. Johnson County. But if you talk about
It's another E, yeah.
Yes.
Okay, sorry.
Yes.
Yes. When I say Juco.
All right.
It doesn't make sense. There's no U.
It's because it stands for junior college. It's generic for any junior college.
Oh. So they think it's because of Joko.
Well, you think it's because.
That's what they think.
Gotcha.
You know what I'm saying?
All right, so we end up with another 1 to the infinity.
Dude, I don't.
But again, this natural logarithm strategy will work with any of these exponential indeterminate forms. So whether you have 1 to the infinity, 0 to 0, or infinity to 0, you're going to hit them with the same idea. Define a new dummy variable. Take the logarithm of both sides. Natural logarithm, my bad. Use the exponent rule, evaluate the limit. Hey, this one's already pre-made into a ratio for you. You can just multiply together. You don't have to do anything weird. Check the indeterminate form before using L'Hopital's rule, but 0 over 0, so we're good. Let's see, natural log becomes 1 over x, and then this one just becomes 1. You plug in 1, you get 1 over 1 over 1. Hooray! So then bring it back to the thing you started with.
Yeah, no, this one.
And to finish, you have to get out of that natural logarithm because you did not actually find the limit you set out to. You found the limit of the natural logarithm of the thing that you started with. So this one also came out as E, but it did not have to. So it's probably a poor example choice on my part for them having the same answer. It's very easy to get E to any other exponent. E to the negative 1, E to the 0. You can get E to the 0, which actually makes the answer 1. E squared, any of that stuff. So. That's it. The time is yours. Whoops. Someone had their... Did you have your hand up? Someone had their hand. Christine, you had your hand up?
Why didn't you do low D high, high D low?
With L'Hopital's rule, you specifically treat the numerator and denominator as separate functions, and you derive each of them individually.
So you can do DFT and FDT.
You have if one of the functions is a product of multiple things, you will. But specifically, the way the rule was written is you treat your the thing you have that you're trying to evaluate the limit of as two separate functions, which you derive individually. And again, if one of those had a product or a chain or a quotient, which would be weird, but I guess it could happen, then you'd use those rules respectively. Whoops, too far.